Hello everybody, welcome back to the channel. I'm here with an A-level chemistry head start video. In this video I will take you through ionic compounds in terms of how they form and actually what they are and some of their properties as well. I'll also explore how you work out the formula of an ionic compound in a variety of different ways, and we'll make sure that we make it challenging and we teach you new things as well as what you needed to know at GCSE level. Hopefully you watched my Head Start to A-Level Chemistry video about atomic structure, so you've reminded yourself about what atoms are. And so if we take a look at, say, lithium and fluorine with these numbers, you should be able to tell me how many protons and neutrons and electrons each of these has, and having done that, you should be able to tell me what the electron arrangement is for both of them, and that's here. Now, ions are atoms that have done something a bit different. So you'll notice here that the protons and the electrons are the same. For lithium, 3 positive protons, 3 negative electrons. For fluorine, 9 positive protons, 9 negative electrons. Well, what happens for ions is the protons and electrons are not the same number. So if we take lithium, but this time lithium has got 3 protons and only 2 electrons, that means that there aren't enough negative electrons to cancel out the positive charge of the protons. So overall, lithium will have a 1+ charge. And similarly, if we've got fluorine, but this time it's got 9 positive protons and 10 negative electrons, the overall charge of fluorine will now be 1-. And in fact, it's not an atom anymore, it is an ion. And so we call it a fluoride ion, IDE. And so this is a description of what ions are. They don't have the same number of protons as electrons. And the reason that that's come about is that electrons have been transferred between atoms. Hopefully you also remember that atoms form bonds to other atoms in order to get a full outer shell or a full outer energy level of electrons. And for the most part that means a full shell of 8. But in some situations it means actually only 2. If we look back at lithium and fluorine in the previous example, what we can see is that lithium has emptied its second shell, and so its first shell is now full, and it's only got 2 electrons in it, whereas fluorine had 7 in its second shell and now it's got 8, so its outer shell is now full. So one of the reasons that atoms become ions is to obtain a full outer shell of electrons. Being more specific then, ions have got a different number of electrons to protons, and they've probably done this to obtain a full outer shell of electrons. And so what must have happened for this process is that electrons have transferred from the outer shell of one of the elements to the outer shell of another, like our lithium and our fluorine in the first example. And the general rule is that the metals, which are all of these elements to the left of that set of stairs, so about 3/4 of the periodic table, those elements give away their electrons in their outer shell. And what that then does is those electrons transfer across to the outer shell of the non-metals, which is this smaller section up here. And so, for instance, in the lithium fluoride example, we can see that this outer shell electron from lithium moves across to the fluorine, and it's therefore absent in lithium's second diagram. So this is the lithium ion on the right-hand side. Whereas the fluorine had 7 of its own dots, it's now gained the cross from lithium's outer shell, and so the right-hand side is showing that fluorine now has an outer shell of 8 electrons, and it's an ion, so it has become the fluoride ion. So electrons have transferred from the outer shell of the metal to the outer shell of a non-metal in order for the full shell to be achieved. Now, a few patterns in the periodic table to remind you of. The noble gases already have that complete energy level, so they don't form ions. And then it's the position in the periodic table that tells you what type of ion an element will form. So for instance, the elements in group 1 with 1 outer energy level electron will throw that 1 electron away and become a 1+ ion. Group 2 will form a 2+ ion. Group 3 will form a 3+ ion if it bonds ionically. Group 4 typically bonds covalently rather than ionically. Group 5, well, it's got 5 electrons in its outer energy level, so they need to gain an extra 3 to become 3 minus ions. Group 6 will form 2 minus ions very readily, and group 7 will form 1 minus ions very readily. So you can work out the charge of an ion a particular element will have from its position in the periodic table. And not only that, you can actually work out whether or not it will be ionic simply by looking at the formula or even the name of a particular compound, looking for those elements in the periodic table. So potassium oxide, for instance, well, you look over on the left-hand side and you find potassium, and then you look for oxygen and you find it over here, and you say, right, well, that's a non-metal bonded to a metal, so that will be an ionic compound. And so that's how you can decide whether something is ionic or covalent, simply by looking at the position in the periodic table. Metal reacting with non-metal will lead to an ionic compound being formed. And when you make an ionic compound, what you actually form is what's called a giant ionic lattice, or sometimes just an ionic lattice for short. And what you've got is a very close packed regular arrangement of ions. And so you've got positive ions and negative ions, and they are surrounded by each other. Notice if we pick this positive ion in the middle, we can see it's got 4 negative ions in the up, down, left, right positions, and they are held together by very, very strong attractive forces called electrostatic attractions. But it's not just in those 4 positions. There'll be another negative ion in front of this positive ion, or above it from our point of view, slightly closer to us than that ion. And there'll be another one moving into the screen. And so in all, there'll be 6 ions surrounding each individual positive ion, 6 negative ions in all of the 6 different directions. And so what that leads to is a very, very strong structure with many, many ionic bonds. And the ionic bond is that electrostatic attraction between these oppositely charged ions. And I've drawn this in 2 dimensions, but you can easily expand this picture to be in 3 dimensions, and that just gives you a bit of a feeling about quite how strong these attractions are and how many of them there are, and that will very definitely affect the properties, which we'll talk about in a minute. But one last thing to mention whilst I've got the picture of the lattice drawn here is that the lattice shows us that there is 1 positive ion for every 1 negative ion. So this could be for something like lithium fluoride, like I keep mentioning, using that as my example. And you can see that the ratio is 1 lithium, the positive, for every 1 fluoride, the negative. It's not always just simply a 1-to-1 ratio, but that positive ion to negative ion ratio is what gives us our formula of LiF, or NaCl, or MgCl2, and more about formulas in a little bit. And so to clarify, this is what an ionic compound is, and the ionic bond is the attraction between those ions. And to clarify how the ionic compound forms, well, that's what we showed earlier in terms of the electrons transferring from lithium's outer shell to fluorine's outer shell. There are 3 main properties that ionic compounds have that you need to be aware of, and they are all physical properties. And so the first one is the melting point. Now remember, in order to melt a solid, what you have to do is you have to overcome the forces holding that solid together. So in other words, the forces between the particles. Now I've already mentioned that the particles in an ionic compound are held together by these electrostatic attractions. And so each of them individually is a very strong attraction, and there are lots and lots of them. So what we have to do is we have to pull that positive ion away from the negative ion, and that takes a lot of energy. And then we have to pull the next ion away from its oppositely charged ions. And so again, each one of these requires a lot of energy to break, and there are lots and lots of them, a huge number of them, in a 3-dimensional lattice. And so the melting point of ionic compounds is very, very high. That's obviously a generalisation, because not all ionic compounds will have the same strength of lattice. And the strength of that ionic bond is dependent on the strength of the attraction between the ions. And that can vary, because if an ion has a bigger charge, for instance Mg2+, then it will have a stronger electrostatic attraction for negative ions than, say, the sodium 1+ ion. So in general then, the bigger the charge on an ion, the stronger the attraction between the ions will be. And that will therefore in turn mean a higher melting point for the ionic compound. Another property is the solubility of an ionic compound. And mostly ionic compounds are very soluble in water. And that's because a water molecule is slightly polar. And what that means is that the oxygen is actually not completely neutral. It has a partial negative charge, and the hydrogen atoms are slightly positively charged. And so what that means is that any ions, so for instance this positive ion here, will be attractive to the slightly negative oxygen atom within a water molecule. And so what happens is this ion gets pulled away and surrounded by water molecules. And this ion also surrounded by water molecules. And gradually the lattice will get broken apart fully, and each of those individual ions that have been broken away from the lattice will get hydrated. It will be surrounded by water and new attractions will form. But that doesn't happen readily in all cases, because remember, those electrostatic attractions are really strong. But these new attractions to the water outweigh the energy that needed to go in to break those attractions. So overall, ionic compounds are generally soluble. This brings me to the final property of ionic compounds, and that is electrical conductivity. Now remember, electric current is the flow of charge. Now that might be electrons through a structure, or it might be ions. Any of those moving charges are electric current. Now, in an ionic lattice, the ions cannot move because they are held together. They maybe vibrate partially about a fixed position. But once these ions have dissolved in water and they have fully separated away from the lattice and they're surrounded by water molecules, these ions are free to move. And so when they're dissolved, these separated ions can move towards their opposite charge. So all of these negative ions would move towards a positive electrode, and all the positive ions would get attracted towards a negative electrode. And these moving ions are an electric current. So ionic compounds conduct electricity when they're dissolved in water, as I've shown here, but also when they are molten, in other words, when they've been heated up to become a liquid. Working out the formula of an ionic compound is something that needs to be really comfortable for you at A-level chemistry. You might be required to work out a formula, or more than one formulae, which is the plural, for no marks, but it will be an important part of a question that you're being asked to work your way through. And so there's three ways of working through an ionic formula that I'm going to show you now, and ultimately they all end up with a ratio of those positive ions to negative ions. For instance, NaCl, 1:1 ratio, MgCl2, 1:2 ratio. The first one is what I'm going to call the electron transfer method. So, for instance, if we have magnesium chloride that I've just mentioned, magnesium needs to transfer electrons in order to get a complete outer energy level. So currently, if we just go to the GCSE notation of 282 for its electron arrangement, you can see those two electrons in the outer shell need to be lost. So magnesium needs to transfer away 2 electrons in order to get a complete inner energy level, which has become its outer energy level. Whereas chlorine is 287, so it needs to gain 1 electron to get a full outer energy level. Clearly, magnesium cannot lose 2 electrons if chlorine is only going to gain 1. And so what we need is a second chlorine atom also gaining that electron. So 2 chlorine atoms have formed 2 chloride ions, and so the ratio then is 1 magnesium to 2 chlorine, and 2 chloride ions is what they become. And so the formula of magnesium chloride is MgCl2. The second method is similar. It's the lowest common multiple method, and that relies on you working out what the charge of the ions will be. So magnesium is in group 2. It will be 2+. Chlorine is in group 7, so the chloride ion will be 1-. And so the lowest common multiple of 2 and 1 is 2. Magnesium is already at that multiple, 2, so that means we only need 1 magnesium. Chlorine, though, chloride, is 1-, so we need a second one of them. So the common multiple there is we need 2 of the chloride ions, so the formula is MgCl2. So you can see we get the same formula whichever method we use. The third method is often the method that people prefer at GCSE level, and it's fine to continue preferring it now, and that's called swap, drop and simplify. The method only has 3 steps. It will not steer you wrong, and it is probably easier than the other 2 methods. So we start by saying magnesium is 2+ and chloride is 1-. Then comes the swap. We swap the 2 and the 1 over, and in that swapping process we drop the positive and the negative charges, because ultimately formula should not have any charge left over, so we might as well drop them at this stage. So we've swapped. The Mg now has the 1 and the Cl now has the 2. And then we drop the numbers down because they need to be small numbers in the subscript position, so much smaller than the symbol for the ion itself. And then comes the simplify, and the simplify has got 2 jobs. First of all, get rid of any 1s. So where we've got Mg1Cl2, we don't want that 1. And so our final formula then is MgCl2. Once again, this third method obviously gives us the same formula. I said there's 2 reasons why we simplify, and that comes about if we have something else, such as magnesium oxide. Magnesium oxide has got magnesium, which is 2+, and oxide, which is 2-. If we swap those 2 and 2 over, and then we drop them down to the line, we then get Mg2O2. But remember, the formula is just simply the simplest ratio, and the simplest ratio of magnesium to oxide is not 2 to 2, it is 1 to 1. So that simplify is a reminder to do 2 things. Get rid of 1s, because we don't bother writing 1s in a formula, but also to get rid of any numbers that are the same as each other. So if we've got 2 to 2 or 3 to 3, we need to simplify it down to 1 to 1. Sometimes you can't work out what charge an ion will have simply from its position in the periodic table. And typically what I'm thinking about here are the transition metals. One of their characteristics is that they can have different charges, Fe2+, Fe3+, Cu2+, Cu1+. And so what we need to be told is either simply what is the charge of that ion, or we need to be able to work it out from the name of the ionic compound. Obviously, if they tell us it's Fe2+, then the method becomes exactly the same as before to work out what the formula of iron chloride is, if we know that the iron is 2+. Alternatively, they might expect us to unpick it from a name, and the name might be iron 2 chloride, with a Roman numeral II inside brackets after the iron. That tells us what the charge of the positive ion is. It's called stock notation. That's a rule. You can look that up if you want to learn more about this. But the rule's operation is it always tells us what the positive charge of an ion is. It's not used for negative charges. And it always belongs to the element that's just been named. So iron 2 chloride has got iron that is 2+, and chloride, which is from group 7 and therefore 1-. And so the formula of iron chloride will be exactly the same as magnesium chloride because the ions carry the same individual charges. So FeCl2, just like it was MgCl2 previously. Similarly, if it was copper 1 oxide, you know that the copper has got a 1+ charge, and oxygen is in group 6, so oxide will be 2-. And so if we swap, drop and simplify, or any of the other methods, we get Cu2O as our formula for copper 1 oxide. And the last thing I would like to look at is that sometimes ions are actually more than made up of just one element, and these are usually called molecular ions. Now they come as positives or negatives, but mostly they are negative. And so, for instance, you can see that we've got the ammonium ion, which is NH4 1+. So there's actually 5 atoms in that ion, but it's got a 1+ charge overall. And the sulfate ion is SO4 2-, so 5 atoms again. Carbonate CO3 2-. So there's 4 atoms wrapped up in that 1 2- ion overall. Others that you might encounter: hydroxide, OH 1-, nitrate, NO3 1-, hydrogen carbonate. Again, 5 different atoms, well, 3 oxygen, 1 carbon and 1 hydrogen, carrying a 1- charge overall. How you work out the formula of an ionic compound which has got some of these molecular ions is exactly the same as before. So if we had potassium nitrate, potassium is K1+, nitrate is NO3 1-, the common multiple there is 1 and 1, so it would just simply be KNO3. Copper hydroxide, copper 2 hydroxide, copper is 2+, hydroxide is 1-, so the formula would be CuOH2. This time it's a little bit different because we need a bracket around the hydroxide to recognise that it's not just 2 of the hydrogen, it's 2 of both of the oxygen and the hydrogen combined together. And then a more complicated one, we might have ammonium carbonate. Ammonium is NH4 1+, carbonate CO3 2-. So we can see, if we look at the common multiple of 1 and 2, it's 2. So that means we need 2 of the ammonium ion and only 1 of the carbonate. And so we'd write NH4 inside brackets, little 2 after that, and then CO3 afterwards. And that's the formula of ammonium carbonate. And just to repeat, we need that bracket around the ammonium ion's formula, because if we didn't, it would simply look like we had 42 hydrogen atoms, and that's not what we're saying. We're saying we've got the ammonium ion, NH4, in a 2-to-1 ratio with the carbonate. There's 2 ammonium for every 1 carbonate, but there'll be thousands of both. Okay, I hope you found this Head Start video useful. If you want to find out more about A-level chemistry for this topic, check out some of the links in the description. If you found it a bit tricky and want to go over this topic a little bit more slowly and in more detail, I'll put links to my GCSE explanation videos in the description as well. But that's all for now. I'll see you again soon.